are?
Yeah.
Indonesia.
I'm from Indonesia. Yeah.
Yeah.
Perhaps your question will be answered next in the, I think on the Thursday, yeah, about the trigger plot presentation clearly over there. But all in all, I think the conversions research right now is still underway, and we are trying to manage to submit some kind of safety analysis report to Bapeten, but it's not yet achieved right now. But yeah, we've developed the safety analysis report and proposed some kind of fuel core management strategy as well, specific for trigger plot reactor. Yeah, a lot of research here, but yeah, still ongoing until right now. Yeah.
Yes, thank you. So we expect your presentation on
Thursday.
Thursday, yeah.
Good.
Yeah.
Okay. Yes, thank you. And next presenter is from Indonesia.
Yeah.
Yeah.
I will present, I think. May I share my presentations? Okay. Can you see my presentation here?
Yes. Yes, please.
All right. Good morning, ladies and gentlemen. My name is Syaiful Bahri. Actually, I'm with my colleagues here, Ms. Nailatus Saada, Mr. Muhammad Subukti, Mr. Muhammad Imron, and Mr. Umar Sahibul Hidayat. They are from 3 research reactors in Indonesia, because we have 3 research reactors in Indonesia. I'm trying to manage, present all the 3 research reactors, but briefly, perhaps in detail, we can go with the discussion for each research reactor with these guys. For example, Ms. Naila Tusada, she's responsible for the Triga Bandung reactor, and Mr. Muhammad Imran and Mr. Purwadi, he's in here as well. He's responsible for MTR RSD gas research reactor 30 megawatts, and Mr. Umar Sahiful is responsible for Triga Kartini. Okay, little bit information about my institution, or National Nuclear Energy Agency. I believe that you are a bit familiar with this, but I'm trying to cover up again. We are basically under the Ministry of Research and Development right now, and the chairman of Batan has 3 deputies here: Deputy Chairman for Nuclear Science and Technology Applications, Deputy Chairman for Nuclear Energy Technology, and Deputy Chairman of Nuclear Technology Utilizations. And we had 3 research reactors. The first research reactor, Triga 2000 reactor, that's operated under the Center for Applied Nuclear Science and Technology, and the Center for Accelerator Science and Technology operate the Kartini reactor. I believe you've listened to the presentation yesterday about that. And the Center of Multiple Purpose Reactor, they are operating the 30 megawatt research reactor. Okay, and this is the location of our research reactor. We had 6 research facilities, basically. The headquarters in Jakarta, and we had the nuclear complex in Pasar Jumat, and we had also the exploration complex in Kalan, that's in the Borneo Islands, next to the Malaysia. And on the southwest of Jakarta, we have nuclear complex Serpong. It's about 40 kilometers from Jakarta. And in the center of Java Islands, this is the about 200 kilometers or 400 kilometers, I think, from the nuclear complex of Serpong. The center of Java, we have a nuclear complex Bandung. In the Bandung, about 200 kilometers, yeah, nuclear complex Bandung. And we had a Triga 2000 reactor over there. And the center of Java, we have nuclear complex of Yogyakarta with the Kartini reactor. And this the reactor in Indonesia. First is Triga Mark II. The location in Bandung, I already mentioned about this before, and it's operated in 1964 with the power of 250 kilowatts and increased the reactor to 2000 kilowatt in 2000s. But right now they are operated at 1000 kilowatt. And the function is basically for research and production of isotopes, and renewal of operating permits was approved until 2026, and safety periodic review has been granted until 2022, if I'm mistaken. And then the reactor Kartini is the location in Yogyakarta. It is operated in 1979, about 100 kilowatt reactor power, and the function is research and training of reactor operators as well as for internal reactor regulatory. This is the most interesting, I think. And then the operating license renewal of the operating permits was approved in 2019 for 10 years. And the last one is in the Serpong, Tangerang, about 40 kilometers southwest of Jakarta, operated since 1987. The power is 30 megawatt, and function is mostly for research, isotope production, and material testing. The operating license is until 6 December of 2020, this year. So next month, this month, I think, yes, next few days. But the renewal of rights have been granted until right now, but we're still waiting the paper of approval from the regulatory body. In subject of period of safety periodic review every 5 years. And talk about the research reactor in Yogyakarta. You may know yesterday that the presentation talked about the Mr. Umar explained that the utilization is mostly for promotion of online distance experiments for using a laboratory, reactor laboratory, and then online distance experiment also with other universities such as Unsri Palembang, and as well as with United Emirates Arab, with another collaboration as well with another 6 universities, I think, nationally and internationally. For the Serpong facilities, we have several facilities, for example, for material characterization, such as neutron diffractometers, neutron spectrometers, neutron radiography, and also we have here neutron activation analysis. So we have 1 CIP irradiation facilities, 4 IP, and we analyze samples such as food, soil, biological stuff, rock, blood, and other agriculture thing. And for neutron radiography, the utilization is mostly for material inspection, such as for industrial product, archaeological sample. And this is the most prominent right now for the gemstone collaborations. So we have outcore irradiation facilities. We produce about 17.5 kilogram until 50 kilogram per month for the gemstone orthopas coloration. Yeah. So we have in-core facilities as well for this. And for the training education, we have training for operator and maintenance technicians, nuclear emergency preparedness, dissemination technology, and nuclear for the public as well. Okay, this utilization I've talked before for neutron activation analysis and radioisotope productions and neutron radiography and power RAM test here. And this is the nuclear complex in Serpong. Basically, we had around 25 hectare, around 800 employees as well. And we have nuclear waste management facilities, RSG reactor, Center for Radioisotope Processing, nuclear fuel element factory. Someone from the audience asked about the fuel factory. Yes, we had here nuclear fuel factory for MTR plant, and nuclear engineering facilities as well, of general workshop and center for nuclear reactor technology and safety, and other management of Batan areas. Let's move on to a little bit about information about the operation schedule of our research reactor. This will give you a bit of flavor of our information about the what is activity here before the startup of the reactor. For example, we inspect the fuel and doing some kind of calibrations and measuring the roadblock tests, for example, like that. This is an example of operating schedule of Kartini research reactor, and this is the example of operation schedule for Triga 2000s. Yeah, you can see here that the reactor operation period is organized in 3 days operation every 3 weeks, with 16 period operation as well. And this reactor has with a fuel element type the rods, and the control rod is 5, and core configuration hexagonal around 121 fuel positions. And the next one is the operation schedule of RSG. This is the biggest one right now in our research reactor of our research reactor in Indonesia. You can see here that the reactor operation is divided for each core configuration. Currently, we are at the 102 core reactor operations, and each core configuration divided into cycle. For example, here it's for core 101, we operated between 13th of March 2020 until 25th of August 2020, and we generate total energy 125 megawatt day, and the accumulative total generated energy since the beginning around 62 gigawatt day. With the total cycle for the core 101, around 4,536 hours, or about 189 days. And the shutdown period, you can see here the shutdown period as well, around 148 days or 3,524 hours. Basically, the shutdown period is employed for the refueling, preparation of operating facilities, routine maintenance of instrumentation system, electrical and mechanical, as well as for repair, corrective maintenance of instrumentation, electrical and mechanical system that's experience problem. I mean, that's some kind of corrective or preventive maintenance as well. And the operation period is around 1,004 hours, or about 77.7%, mostly at high power for radioisotope production, topaz radiation experiments, and at low power is only about 6.5 hours, or 0.15%, fueling, criticality experiments, and calibration of control and other preparation process. So let's basically give you an illustration of what is the operation schedule, the standby periods, and as well as the operating period. And the next one is the an example of core configuration for Kartini based on the Triga, and the RSG core configuration for the Triga plat. And you may listen the presentation before for by Mr. Umar. But for the RSG is designed to operate at nominal 30 megawatts, and RSG has 8 control fuel elements and 40 standard fuel elements in 10 times 10 core lattice, as given in the figure. and two fork type of AGI and CD that serve as control the population of neutron irradiated through the fuel elements, and the RSG utilizing silicide fuel, and we have the safety criteria and limitation used in this equilibrium core calculation as well, such as for shutdown margin reactivity, it's minus 0.5%, and maximum radial or peaking factor about 1.4, and maximum discharge burn up 59%, and the number of performance of all irradiated capacities within the core unchanged during the conversion from the oxide to silicides. And you can see here the standard fuel element and the standard control element, beryllium refractor element with the plug as well, and irradiation facilities or IP here, and CIP, the center position of radiation, and we have a pneumatic rabbit system and hydraulic rabbit system. Talk about the regulation of fuel and core management of fuel handling here. We are stick to the Bapeten Chairman number 2, year 2014, on the core management and handling store of nuclear fuel on non-power reactor. The Bapeten Chairman as well referred to the core management and fuel handling of research reactor given by the IAEA Safety Guide and SG 4.3. And the graded approach is applied on a core management, handling, and storage of nuclear fuel based on this Bapeten Chairman number 2 and 2014, because in Indonesia we had 3 different research reactors with 3 levels of different levels of power, different power. The first one, the requirement of this Bapeten Chairman regulation and article number 4 are implemented by applying a graded approach depending on the characteristic of radiological hazard potential of the non-power reactor, and the characteristic of radiological hazard potential as stated in the first one are based on the reactor type, nuclear fuel type, power level, coverage of the utilization. So it's clear here that all the 3 research reactor may use this standard regulation from our regulatory body. In addition, also the application graded approach on OLC, for example, here the characteristic of radiological hazard potential as stated in first one, given by Bapeten Chairman number 9, 2013, talk about the operating limit and the condition of non-power reactor, covers reactor type, fuel type, power level, and coverage of the utilizations. So just give you a little bit information about the Bapeten Chairman number 2, year 2014, article 5. It's cover similar like the IAEA standard here, there, NSG, NSG 4.T. That core management covers core calculations, loading, unloading, and fuel assemblies, verification of the core characteristic over there, and core monitoring, and how to ensure the integrity of nuclear fuels, and it's also important here the procurement of nuclear fuel and core components, and for the handling and storage of fuel, handling and storage of fresh fuel is covered here, handling and storage for irradiated fuel, handling and storage of core components, and fuel cache before transport the fuel. And I give you the example of the standard operating procedure. So basically all 3 reactors referred to the Bapeten Chairmans. Then the Bapeten Chairmans, as I mentioned before that clearly mention the emphasize the validation method and codes should be used and to be determined appropriately over there, and the integrity of fuel assembly should be ensured as well, and the reactor core should be monitored, and integrity of the cladding of fuel assembly should be continuously monitored as well. All of them is covered on the Bapeten Chairmans I've mentioned previously, and this is the standard operating procedure procedure for the Kartini reactor. This is only the example, one of the example, number 104. It's cover personnel tool, core calculation, loading, unloading fuel assemblies, verification of core, similar with the Bapeten chairman regulations, and core monitoring, ensuring the integrity of nuclear fuel, and procurement of nuclear fuel and core components. And the calculations here in Kartini using MCNP and TRIGAP concerning validate input value and benchmark as well, and keep up to date and comply with the OLC and safety analysis reports. And for the loading of fuel assemblies, the SOP of fresh fuel loading using handling tool as well is covered here. And for the irradiated fuel, the process of loading fuel into the core follows the SOP. And concerning standard, the operation procedure for loading fuel from bulk shielding to the core and transferring of fuel out of the core follows another SOP, namely the standard operating procedure for loading fuel from bulk shielding to the core. And for the verification of core characteristic is carried out by withdrawing and insertion test of each controller in accordance with the SOP as well, number of 37, and the testing of controller drop time. We have a calibration of control time as well, and the calibration of control load according another SOP as well here, and shutdown margin testing with the according to safety analysis report of Kartini chapter 5 and 17, and flux neutral mapping and power calculation also was performed here. Yeah, and for the this is another example for core management of TIGA. The standard operating procedure for application is implemented here based on the Bapeten chairman as well. And the core management of TRIGA here, it's mentioned that the 3 activities basically: safeguard activities, management of nuclear material accounting. The routine reactor operation period is 3 days per 3 weeks, and fuel fraction is calculated every 3 months and reported to Bapeten as well. And the calculation is done based on the MCNP on origin in MOPCCS package, and fuel accounting is routinely recorded and reported annually. And the core management activities such as reshuffling, refueling, when the reactivity of core decrease, the reshuffling or refueling activities are carried out. The reshuffling is done by shifting all the fuel elements, the core with the particular patterns to increase the reactivity while still complying with the LCO. And the next is about surveillance of activities, go, no go, visual observation and testing. It's performed as well in the TRIGA reactor 2000 in Bandung, and monitoring the potential of grading changes using go, no go device, and radioactivity monitoring of tank water using sipping test technique, and visual observation of a fuel element using underwater camera. And the management for TRIGA 2000 fuel storage facility as well covered here, storing new fresh fuel at the fuel element warehouse facility using a treatment rack that is arranged in such a way that the accident not occur over there, and arrange the core configuration in such a way that fuel element can achieve criticality when the reactor is operated, and storing the used fuel element in the bulk shielding facility filled with the water as radiation sealed medium, and storage as well as for the fuel, the use of fuel element storage at spent fuel storage pit facility. And for the RSG reactor, this is the big ones. I'm just give you some of standard operating procedure here to give you a flavor that the RSGs cover all the aspect of core management and fuel handling. For example, here we have standard operating procedure for the calculation of refueling of RSG core. The core model, the pattern, it's 5 ones using Batan's fuel program, and standard operating procedure for new working core. For example, here arrangements, and standard operating procedure for fuel element reactivity measurements, standard operating procedure for removal of standard fuel element and control element for the refueling. And another one, for example, here the standard operating procedure for standard fuel receiving element. So when the fuel is coming to our facilities, we perform a standard operating procedure to inspect the fuel element and control element until it's stored in warehouse, and then standard operating procedure for flux neutral measurement, how to measure the flux, and standard operating procedure of storing spent fuel, and standard operating procedure of storing fresh fuel in the fresh fuel warehouse as well. And the last one is the standard operating procedure for maintenance of fresh fuel warehouse, and the standard operating procedure for removing spent fuel from RSG to interim spent fuel. So basically it's all covered here, and our research reactor RSG especially have a 5-1 pattern, which means that after the burn up is the highest burn up is reached, 5 fuels and 1 control are removed and then replaced with another 5 fuel and 1 control route. So that's basically the procedure with the standard